Well, hello everyone. What I'm going to do in this lesson is to show you how you can use your TI calculator, typically your TI-84, to solve questions involving the normal distribution. So what I've got here are some worked examples with the question and some screen grabs of what it would look like. The PDF of this will be online in about an hour or so from now, and you'll be able to watch this video as well. So let's look at our first example. According to survey data, the distribution of arm spans for females is approximately normal, with a mean of 65.6 and a standard deviation 3.2 inches. So if you took a typical woman, she stretched her arms out from one side to the other, it's about 5'6" from tip to tip, but there is some variation. I'm assuming, but there's no guarantee, is that perhaps taller women have longer arm spans than shorter women, but that isn't always the case, of course. But in general, these are the average and standard deviations. So we have a very straightforward question to answer here. What percentage of all women, assuming adults, have an arm span of less than 60 inches? Well, we can actually calculate that, because essentially what we're trying to do is find out what percentage of people have 60 inches or less in a normal distribution with 65.6 inches as a mean and a standard deviation of 3.2. So I'm going to go over here and type in how you would get that calculation. And here's a screen grab of what it's going to look like. So you hit the blue button and you get this guy called distribution. So blue button, distribution. And the one that you want to choose is number 2. Then you hit enter. Now it's going to ask for a lower value. They've got a number in there, but I'm going to just pick my own. Negative 999 is a good placeholder for the lowest number you could ever imagine. So when you want a less than situation, this guy here, the lower number, is negative 900 and whatever you feel like. Enter. Now you want it all the way up to 60. So what these two things tell you is that you're looking for things 60 or less. That's what the question was. Now that funny little Greek letter there is the mean. It's mu, it means the mean. In this case, 65.6. And then we have a standard deviation, and in this case it's 3.2. Now if you look over here, you can see my screen grab was of this. So all I do is hit enter one more time and a third time, and the value that comes out as a decimal is this guy. If you round it off, you get 4%. So you have now found out that, surprisingly enough, only 4% of all women have an arm span of 60 inches or less. Now let's move on to our second example now then. The average daily temperature in a particular city has a distribution that is approximately normal. Well, think of approximately normal means if you took all the data in all the different years that you collected it, it would look like a single hill balanced in the middle. So it would go up and then it would come down, just like a normal bell-shaped curve. And in this case, the mean of this place is 58.2 and the standard deviation is 7. And we're being asked to calculate what percentage of days in this city have a temperature of 45 or warmer. So now we don't want, like the previous example, to be less than something. In this case we want it to be bigger than something. So how do we adapt? Well, the general format is the number you want and then some ridiculously big number like 999. In the other case, remember, it was a ridiculously small number like negative 999. And then you type in the mean and the standard deviation. So let's see what that looks like. Blue button, distribution. Number 2. So scroll down to number 2, hit enter. We want a low number this time of 45. We want a ridiculously high number. Now those two guys together are describing 45 or above. Anything from 45 on the low side to the end of the universe on the right hand side. Bigger than 45. Now in this story the mean is a new number, it's 58.2. The standard deviation is a nice number, it's 7. Notice I'm hitting enter each time and then I hit enter on paste. That's basically the calculation. We hit enter and it comes out to about 0.97 and change, 0.9703. So we have that the percentage of days in this city that have a temperature 45 or warmer is 97.03. So you can imagine if you actually lived in this city, you're probably never going to see snow, like maybe once every few years. It's a rarity. Quite a nice place to live actually. Now this next story is actually real data. The average IQ of a Scottish person is 100, and the standard deviation of all IQs, at least these type, are 10. And they're asking you to find what percentage of Scottish people have an IQ between 85 and 100. So this is the third kind of situation. The first example we looked at being less than 60, the second example being bigger than 45, or whatever it might be. In this case we want a between. So when you do that, you want the low number first, comma, the high number second, followed by the usual mean and standard deviation. So let's see how that works. Second, distribution. Number 2 again, the normal CDF. And I want numbers that are between. So they start at 85, the small number, and they finish at 105, the big number. And the mean, the new value is the mean, is 100. And the standard deviation, that little sigma, the standard deviation, 10. Now do you see that's a good screen capture of what I have here? So when I hit enter, we get this, and then I hit enter, and I got 6247 if you round it off, about 62.47%. So slightly more than 60% of Scottish people have an IQ in this range. So that's a typical kind of middle of the range kind of set of intelligence quotients. Let's look at our next story. Right, they're coding it, so let's tell you how they code it. The normal model, that means that this distribution of the length of pregnancies is a classic single hill, unimodal, symmetric, all the good stuff, and therefore we can use this process. The n means normal. 270 means the mean is 270, and 9, the second number, means standard deviation. So if you wanted to know of going into spontaneous labour, right, so that's just, for want of a better word, natural labour, right, it's not being induced chemically or otherwise. So if you just left women to do it on their own, this is the kind of distribution you'd get. It takes them about 970 days, so it's about 9 months, seems reasonable. But there is a lot of variation, right? Some mothers have children earlier, some mothers take a little bit longer, and in this case the standard deviation is 9. So question A says, how many days will a woman need to take to go into spontaneous labour to be at the 60th percentile? So we're kind of figuring out what number would you need to be in the 60th percentile. That means everybody before and up to you, that's 60%. So from the earliest up to whatever this missing number is, 60% of all pregnancies take. Well, that involves a new guy. It's called the inverse norm guy. Because what we're actually calculating here is a number that corresponds to a 60th percentile. Right? So, blue button, distribution. But number 3 now. Inverse norm. I know it's got a funny name, but that's its name. Now the area that they're calling the area represents the 60th percentile. 60th percentile as a decimal is 0.6. It means 60% or less. So I'm typing in 0.6. Right, there we go. The mean is 270. The standard deviation is 9. And it's best just to leave this thing alone. It's always on left, so leave it on left. And then hit down to paste. So you see that that's the picture. There's my screen grab. So when I hit enter, it will do the calculation, followed by roughly 292, 272. Oh, I see what I have done wrong. And do you see that this guy here is 290 and it should have been 270? Okay. Right, I'm going to go back and redo this calculation just to show you what it should be. So I'm going to do number 3, inverse norm. Oh, there it is. 0.6, 270, 9. Oh, I did it right the first time. Okay, we're cool. So I will make sure that that screen grab is replaced by the proper one. So, okay, 272.28, 272 days. Now for the next one, how many days will it take, will it need to take to go into spontaneous labour to be in the top 10%? So we're trying to find out here, what is the maximum, what's the top 10% is like the 90th percentile, right? If you're in the top 10, 90% of the people are below you. That's essentially how you think of it. So I'm going to choose number 3, and I'm going to have to change this data to suit the real data. So we are looking at a 90th percentile, that's fine. This guy here is 270, that's good. This guy here is 9, that's good. And then go down and hit paste, and the answer we get is 281 days, which, if I think about it, is much more realistic. So far so good. Let's continue then. Now this last one is a story to do with blood pressure. The mean systolic blood pressure for males is 113.8 and their standard deviation is 10.8. So let's suppose you're categorised as extremely low blood pressure when your value is in the bottom 10%. What would that blood pressure be? Right? So what would you need to have to be in the bottom 10% of low blood pressure? So that's 10th percentile essentially. So second distribution. Go to number 3, inverse norm. Now I want to be in the 10th percentile, so 0.10, right? The blood pressure has an average of 113.8, check. The standard deviation is 10.8, check. Leave that guy alone and go to paste. So this one matches the screen grab, that's good. Enter, enter, and pretty much I've rounded it off, but it's pretty much 100. So if you have a blood pressure, a systolic blood pressure of 100 or low, then you're considered in this example to have extremely low blood pressure. What about the other extreme? Well, let's suppose you're considered to be extremely high blood pressure if you're in the top 5%. So what would you need to have as a blood pressure to be in that place? Well, to be in the top 5%, it's the same thing as the 95th percentile. Right? If you're in the top 5, 95% of the people are worse than you. So let's find out who that is. So to be in the 95th percentile, 0.95, we can keep the mean and standard deviation, it's the same numbers. Keep that guy. And now this matches our screen grab, good. Now hit enter a couple of times, and about 132 if you round it off. So you can imagine how this could be used. Whenever you get blood pressure, potassium levels, whatever it is, iron levels. You know when they do all these various tests on your hormones and whatever it is they're looking for, there is a kind of normal range, right, whatever that is. So they collect a lot of data on just the typical adult population. Males and females are normally treated separately because their blood chemistries are a little bit different. And then they find the mean for that data and the standard deviation. And then you can then put categories on high, extremely high. So when the doctor gets the results back, he doesn't just get told what your blood pressure is or what your potassium level is. He's also given labels that says high or extremely high or low or extremely low, and it's a way for him to just scan through it, or a nurse to scan through it if they get the whole list through and say, well, everything is okay, your blood pressure's a little bit high and your potassium level's a little bit low, and that's okay, that's nothing really too much to worry about, we expect these kind of things. But if you come up with some results that are really in the dangerous areas, right, the extremely high or the extremely low, then you're going to take much more interest in it. The doctor's going to say, okay, you've got something going wrong here. We've got to figure out what it is and then, hopefully come up with a treatment. Now, they need this data to know what is a really high blood pressure, what is a really low blood pressure, right? Or whatever the chemical hormone that they're trying to go against. So I can imagine this kind of information is like bread and butter for the medical profession. They collect information about you and then they compare it to what the typical values are to see whether you're in the normal range or whether you're outside that normal range. Well, this last question is just to show you that sometimes they mix and match them. For instance, the last question is, what would your percentile be if your blood pressure was 120? They're telling you the number and you're trying to find the percentile. So we're kind of back to the beginning of today now. If you are going to be in the 120 mark, 120 or less is the percentile that you would be. So we go second distribution and we find out what percentage of people have your value all the way up to 120. Right? So you start off with a really ridiculous negative number, right, as low as you can think, all the way up to 120. You then type in the mean, which is 113.8. You then type in the standard deviation, which is 10.8. And now we are ready to go. And it's about 717, which is the 71.7th percentile. In other words, 71.7% of the population, male population, would have a blood pressure of 120 or less. So you're a bit in the high side, but nothing, I don't think that would be considered seriously high. Okay, and that is us finished. Hopefully this has helped.